So, hello everybody, my name is Petit. I am a third-year PhD candidate under the joint supervision of José Rouillard and François Cabestaing, and today I'm going to present our work named Design and Study of two applications controlled by a brain-computer interface exploiting steady-state somatosensory-evoked potentials, or 3SEP to be shorter. So first of all, a brain-computer interface is a system that aims at differentiating different state of minds of a user based on his brain activity in order to translate them into different commands to an external system. Now, to give a little bit of context. In our work, we used an EEG-based BCI because the brain activity is recorded with an electroencephalography. And we exploit 3SEP, which occurs when the user received a vibration on the skin. It is characterized as an increase of activity in the brain activity at the frequency of stimulation. The localization of this increase of activity on the scalp depends on the location of the vibration. The amplitude of the 3SEP can be modulated by the user using something called somatosensory gating. The gating is the capacity of our brain to filter out irrelevant or repetitive stimuli. In our case, when the user will perform an motor imagery task, we expect that the 3SEP's amplitude decreases by somatosensory gating. As an example, on the right part of the screen, we illustrate how our BCI works. We start from an initial idle state where the user does nothing and is receiving two stimulations on the wrist, one at a specific frequency like 10 Hz and the other at 20 Hz, for example. And here we can see the respective 3SEPs. And when doing a motor imagery with the right arm, here like a fist clenching, we can see that the respective 3SEP's amplitude will decrease while the other does not. Therefore, by monitoring the amplitude of the 3SEPs, we can actually provide 4 different commands when the user is imagining a movement with the left arm, or with the right arm, or with both arms simultaneously, or nothing at all. But for today, we performed our user experiment with the brain-computer interface being controlled using only sham feedbacks, in order to assess different levels of performance of the BCI and have a sense of how the user experienced each levels. Our objectives were to design game-like applications for BCI with a semi-balanced command usage. This allows us to perform offline analysis in a more relevant way. The second objective was to study the effect of the application on the user themselves. The third objective was to study the correlation between the perceived usability of the system and the performance of the system, therefore allowing us to have a mapping between the BCI performance and the mean SUS score, which finally will allow us to do a prediction of the mean SUS score that will have received our system for a given BCI performance. About our applications. The first application is a card-driven application, and the second is a puzzle-solving application that we called SOCO-BCI. Both applications have a 3-light fire, which gives the different periods between the command selection and the command execution and the breaks. The green light gives the command selection period. It's the moment where the users have to do the motor imagery task. The orange light shows where the application reacts to the classifier's output. The two applications differ mainly on 2 points. We first have a strong difference in inertia. The card is still moving during the red light because the card gains momentum for each action performed by the user, while the avatar is idle during the red lights in SOCO-BCI. Another difference is something we call the punitiveness of the application. the cart will be pushed back on the tracks by barriers on either side of the road, which means that in the case of a mistake, it's not a big deal for the user. The cart will somehow manage to go straight. But for the SOCO BCI, the user must react to provide a corrective command. Now let's describe our protocol. First, we install the BCI on the subject, so the EEG cap and the tactors which provides the stimulations. Then we performed 8 blocks of recordings, 4 blocks of cart and 4 blocks of SOCO BCI, or vice versa, depending on a pseudo-random order. And each block will have a specific sham accuracy ranging from 45% to 90% in a pseudo-random order too. At the end of each block, we give a questionnaire to the user. It could be a behavioral data questionnaire, like how much do you feel awake or fatigue and so on. We also assess the mental workload using a raw TLX questionnaire. And finally, we measure the perceived usability of the system using the system usability scale. At the end of the session, we also have a guided interview in order to discuss of the system with the participants. At the end, we had 10 participants in our study. Now I'm going to quickly present our results. So first of all, the behavioral data. We have 4 dimensions, each assessed on a 5-point Likert scale. We did not observe any difference in awakeness, mood orientation, or emotion intensity. However, the perceived tiredness seems to increase during the experiment. The majority mention shifts from 2 to 3, and we also see some mention 4 appears during the experiment, which said that our experiment was just a little bit tiring, but still manageable. The mental workload level was measured with the raw TLX. For each application and each accuracy, we display here the distribution of the scores using box plots. And we can observe that the raw TLX scores seems uncorrelated to the performance of the BCI, as each distribution are centered around 50. However, when investigating each individual dimension of the questionnaire, we can observe that the self-assessed performance of the user and the experienced frustrations are highly correlated to the sham accuracies. In addition, we did observe a significant difference in the mental demand of the task between applications. Here, we can see that the cart application seems a little bit more demanding than the SOCO BCI as soon as the accuracy reaches 75%, and it can be explained by the presence of inertia in the cart application. It makes the user thinking a lot more about what they are doing and what needs to be done even during the breaks. Therefore, the users must maintain some level of alertness during the entire block. About the relationship between the performances and the SUS scores, here we display the mean SUS score for each applications and each accuracies, and the bar errors shows the 95% confidence interval. We do propose a model of this relationship using a linear regression given here and here. And we use this model with the well-known works from Bangor in collaboration to find the performance required by each application to reach an acceptable mention. We observed that to be defined as an acceptable system, the SOCO BCI would need a performance of 85%, while the CAT needs only a performance of 74%, which is roughly a 10-point difference here. We may explain that by the punitiveness in the SOCO BCI, as during low accuracy block, the mistakes made by the system will be more annoying for the user, hence a lower mean SUS score for low accuracies, which makes, in turn, the slope of the regression steeper. To conclude, we have designed 2 applications controlled by our BCI. We also find a significant difference in mental demand between each application, which could be a good thing or a bad thing if you want a more challenging application or a less challenging one. We also propose a model of the relationship between the performance of the PCI and the perceived usability. As a future works, we would also like to assess our system on a group of patients in order to assess their experience of our applications. Finally, I would like to acknowledge the works of Camille Bordeaux and Philémon Berne, who were helpful interns in our team at the time that this work was performed. Finally, I would like to also thank our collaborator on our broader project, the Professor Arnaud Delval, who is a professor in the Hospital of Lille and allowed us to record the data using their EEG system. Thanks for your attention. If you have any question, this is my email address.